Okay, welcome to the second part of this course. In HEC-RAS study, you can use a Salisbury Van and Wu model, and this equation or this transport functions are not available for 1D, and they are only available for 2D sediment transport in the newly version of HEC-RAS. You can select the sediment transport function sections in the technical reference manual for detailed description of this formula. As an overall, you know that sediment transport functions simulate nonlinear transport processes and produce very different results. Model results are very sensitive to the selected function. Carefully review the range of assumptions, hydraulic conditions, and grain sizes for each method was developed. Select the methods developed under conditions that most closely represent the system of your case study and calibrate results to actual river bed change. For example, if you had two different topographic maps with the time span of, for example, 10 years, you can run the model with the one topographic model and then compare the results after 10 years with the new topographic map for defining or determining the best, transport function. If you don't have two different topographic maps with two different time spans, you can consider the assumptions, hydraulic conditions, and grain size of each formula and consider the similarity between your case study and that model to select better transport functions. The transport functions compute the transport capacity for each cross sections based on the hydraulic or hydrodynamic results. Shear stress, water surface, flow velocity, and fall velocity of the channel. By default, the HEC-RAS 1D model simulates use bank stations to derive each cross section laterally into seasonal zones and two overbank zones. LOB and ROB. The transport functions only use the channel hydraulics. Okay, the sediment transport is completely related to calculating the sediment transport capacity for each cross section. In this window, you can see the setting with the name of sorting method. What is the sorting method? You know that sediment transport compute transport potential without accounting for sediment availability. In many well-graded rivers, a coarse armor layers forms on the top of subsurface layer, composed of representative each gradation. Armor layers decrease total transport because the surface particles available for transport tend to be coarser and more difficult to move. And while if you use only sediment transport functions, it's not to lead to realistic results because, as I mentioned, transport function compute only transport potential without accounting for sediment availability. And they don't consider armoring effects on the sediment transport issues. For this issue, HEC-RAS created and considered sorting methods. This is also physical limiters on transport capacity. And the bed sorting model, sometimes called a mixing or armoring method, keeps track of the bed gradation with HEC-RAS. Uses to compute gradation. And this figure, you can see the schematic representing of mixing layers in HEC-RAS sorting and armoring method. The active layer for subsurface layer and inactive layer for deeper layers. In HEC-RAS, you can use three different method for computing sorting methods. The first one is Thomas or EX5, and sometimes they call that Exner5. This method uses a tree-based bed model that forms an independent coarse armor layer which limits the erosion of deeper layers. HEC-RAS version 45, an earlier version called this method Exner5 and was the default method in HEC-6 in the old version of HEC-RAS. And the second one is Coupland or Exner5. Coupland in 1993 developed an alternate version to Thomas mixing algorithm. This method was designed for sand and sandbed rivers because it forms armor layers more slowly and computes more erosion. And finally, the third version is active layer. This layer, the two armoring methods above I mentioned, Coupland and Thomas, have been successfully applied on many river systems. However, they are complex and can suffer from black box effects, producing results that users have troubling to interpreting that. Both armoring methods also have numerical thresholds that generate gradational non-linearities, introducing noises in the gradational results. Therefore, HEC-RAS introduced a simple two-layer active layer method with the name of active layer. The active layer thickness is set equal to D19 by default. An assumption is only appropriate for gravel beds. However, you can change this default and I explain in the next parts. As an overall, the sorting method is controlled the erosion and deposition process through the rivers and through the cross sections. And without using the sorting method, the sediment transport lead to unrealistic and unacceptable results. One of the most important issues, as I mentioned before you, is the fall velocity method. In some sediment transport methods or function in HEC-RAS, for example, topology, they need to compute fall velocity values. In order to compute velocity values, HEC-RAS consider 8 different methods. For example, Robbie, topology, Van Ryn, report, 12, Dieterich, Soulsby, and Wind method for estimation of fall velocity. I think that in Young and Wilco and topology, we need fall velocity to estimate the transport capacity, and therefore the model provides these options for computing Robbie, for computing fall velocity using different methods. And most of the fall velocity methods requires temperature data, and we entered or defined this value in this editor, in quasi-unstable editor. We entered the set temperature options and define the value of temperature in different duration time. And the model used the temperature data and some other related, some grain size data, and calculate the potential of fall velocity for each grain size. The next part of this tab is related to maximum depth or minimum elevation. You know that HEC-RAS sediment control volumes are centered around each cross section, as depicted in figure 11. Okay, you can see that HEC-RAS used this control volume for sediment transportation simulation. And you should enter the erodible or deposition limits, and the model starts to transport sedimentation for deeper layer and side ways of each cross sections. The user must specify the width and vertical thickness of the control volume. The dotted line in the cross-section plots traces the vertical and lateral control volumes. For better presentation of sediment volume, you should consider these notes. First of all, the maximum depth approach is more common, and most of the engineers and researchers use these options for defining the control volume of sediment transport calculations. With max depth, the user sets the bottom of the control volume to a distance below the original invert of the channel. For example, if the invert of your channel is equal to 10, you can use the max depth about 5 meters, and if you think that the maximum erosion of this river can be reached to 5 meters, you can use max depth as equal to 5 meters. And if you have a erosive or most erosion river, you can select higher values to max depth. Otherwise, if you have a river with a smaller rate of erosion, you can use the smaller value to max depth. As an overall, the value of 10 meters is the best choice for max depth. However, increasing the max depth increase the runtime of model and the instability issues. And the second important note is that mean elevation. Mean elevation sets a hard elevation below which the model cannot erode. This option often simulates non-bedrock control, grade control structure, or volume flume bottom or concrete channel lining. Okay, let me show again. You know that in initial conditions and transport parameters tabs, we have two important columns: max depth and mean elevation. If you have cross sections and you want to estimate the sediment and erosion rates at each cross section, you should set max depth column. Conversely, if you have some bedrock, for example, if your river crossing or flowing through a bedrock, you should enter the minimum elevation value to prevent the model to erosion this area. And you can use these columns for each section, and you can set this value and this value simultaneously, because this means that if you enter the max depth, the model starts to erode and deposit the sediment through this cross section. While if you enter the minimum elevation values for these cross sections, the model only erode and deposit the sediment particles, and the model cannot be eroded lower than these values. I mean, if you want to model sediment transport in reservoir, you should enter minimum elevation column, not max depth, because in dams the riverbed is the minimum elevation, and the situation is related to deposition processes. As an overall, this option or this column is suitable for bedrock or for man-made concrete channels that the bed invert elevation is constant and the model cannot erode the bed elevation. For natural rivers, we almost use these columns and enter the max depths. And if you select this row, you can see that this is the dotted line, represents the sediment transport volume, and the model can simulate the erosion or deposition rate between maximally in this dotted line. And when you select mean elevation, you can see that the volume sediment control is higher than that elevation. And in this case, we can't see any erosion area. Okay. The third and fourth column is related to left and right station to movable bed limits. The station, the left station says that the model can start to sediment transfer process between this area, the lateral limits of sediment control volume. I'd say that each sediment control requires width, specifying lateral movable bed limits in station left and station right columns, which can constrain erosion and deposition to the cross-section node between them. HEC-RAS will only deposit or erode wet cross-section point between these lateral limits by default. Okay, you can enter the suitable values for this cross-section, or you can click on use button. Let me delete these columns. You can use banks for movable bed for presenting the lateral limits of movable bed, or sediment control volume. I click on use banks for movable bed, and you can see the model automatically select the left and right bank station for movable bed limits. Or you can change the value of this station, left and right station, manually. I can for example, I can change this as 1010. Okay, you can see the location of lateral movable bed limits will be changed. Okay. For selecting movable bed limits, you should consider some important issues. As you can see, I select use banks for extend button for setting the laterally or volume or movable bed limits. However, selecting movable limits close to the bank toe can lead to unrealistic cross-section shapes in the positional condition. If you define the movable bed limits near the toe, the model starts to deposition or inversion conditions, and you should select the movable bed limits in appropriate locations to prevent occurring these errors. In figure 12, you can see the movable nodes inside the movable bed limits deposit enough that they end up significantly higher than the immediately adjacent nodes. Okay, after defining the movable bed limits location, you should define you can use multi-bed movable bed limits. This is for a natural cross-section. If you have two or three main channels, you can use multiple movable bed locations. For example, if you have cross-section like this, you can set only one value for movable limits, and you can set for each main channels left station and right station differently. Let me show again in this in sediment editor, data editor. In the new version of HEC-RAS, there are a number of mobile bed channels. In the old version, we only had left and right station, and we couldn't consider the 2 or 3 main channels in the model. If your channels have 2 or 3 or 4 or more main channels, you can set the number of mobile bed channels to maximum 6. For example, if I select second, you can see the models you can set 2 left and right station values for your cross sections. If you have a natural channel with only 1 main channel, you can select only 1 value for them, and you don't need to enter new values for left and right stations values. And in HEC-RAS, we can see we can define different values for or consider main channels, and it leads to realistic and acceptable sediment transport simulation in these cross sections. Okay. Okay, the next step is defining bed gradation, which is important for sediment transport because the model starts to transport the bed gradation materials into downstreams and mix the bed materials in downstream cross sections. You know, each cross section requires initial bed gradation data. I mean, you should enter or you should define bed gradation values for each cross sections. Instead of requiring user to input gradation for each cross sections individually, HEC-RAS uses a template concept, and you can enter or define the bed gradation template and use it for different cross sections. User-defined sediment gradation is a database, and then associated them with, bed gradation templates. In many applications, these templates will correspond to individual bed samples taken into the project reach. Templates are created and edited by define edit bed gradation button. Let me show. In this window, you can see the define and edit bed gradation button. If you click on this button, the bed gradation editor will be appear. And in this window, you should create a new template or new sample. Sample for my sample. And you should enter the value of a grain size for each samples. For example, in HEC-RAS, the default bed gradation class divided to 20 different classes from finer or smaller grain size to larger grain size. Sand, gravel, cobble, or clay, or very fine sand, very fine clay and other bed materials. In this window, you can see 2 options. There are 2 options, finer and grain classes. Finer defines the sample using as a cumulative bed gradation curve with percent finer defined by the upper bound of each grain size. For example, in this figure, the value, the diameter of 4 millimeter represents that about 94% of particle is lower than 4 millimeter. And finally, the 100% of particle size in this sample is lower than 24 millimeter for particle size. Okay, you should enter the values cumulatively, not incrementally. The diameter listed for each grain size class is the upper bound for that of grain class, and value should be entered as percent. And the second option is grain class or weight. The sample fraction of each grain class is specified. These values will be normalized so values don't have to add up to 1 or 100% and can be input as simple masses if preferred. In most case study we use finer, and however there isn't any difference between this option and grain class fraction option. You can use each option if you are okay with that. In this example, you can see the gradation, curve for the left one is a fraction or grain size class, and the right is for finer. In the grain class, you should enter the percent of each diameter for each class, while in the finer options, you should only enter the cumulative values for each diameter. Okay, I think that for this part, this is okay, and I stop the video in this time, and in the next part we will explain about the other options in sediment data editor. See you soon. Goodbye.